Hello everyone. The remaining sections of chapter 1 is graphical summaries. So when you have samples or a population full of data and you want to represent the data graphically, so your client will be able to see the whole picture in one image. You have 5 different methods: stem and leaf plot, the dot plot, histogram, box plot, and scatterplot. The first two is not very popular, so I will focus more on the last three that are used more frequently in the industry and in academia. So the stem and leaf plot basically is used if you have data points that are small numbers and maybe 20, 30, or even 50 data point in the sample. Then what you do is the rightmost digit will be the leaf, and the leftmost digit or the left twomost digit will be the stem. For example, if you have a sample of 34, 21, 51, 61, 61, and so forth. Since these are two numbers, the stem will be 0, 1, 2, 3, 4, 5, 6, until 7, 8, 9. And the leaves, for example, 51, that is 5, there is 1. Let's assume here we have also 56. Then there is 5 and there is a 6. And 61, I have 1. I have 61 again here. So I have 1. 21, it will be 1. Do I have another 21? Let's say we have here 25. Then I will have another 5. So by looking at the stem leaf plot, I can tell what kind of data point I have in the sample. For example, if I look here, I have 42, 45, 49. I have also 50, 51, another 51, another 51, another 51, 53, 53, and so forth. Again, this method, stem and leaf plots, is useful for a small sample, and you can represent it in this format. Let's say you have, for example, then data of 3 digits like 216, 219, 351. Then these two will be the stem and this is the digit. Then you will have 21, 6. You have another 21, so that will be 21, 9. And you have 35, 1, and so forth. So then the last 2 digits will be the stem and the third one will be the leaf. The dot plot also used for small samples. In the x-axis or the horizontal axis, you divide it using the smallest value of a sample, in this case let's say 40, and the highest value of a sample of a data point in the sample, in this case is 100. Then you place dots. If there are, like, for example, the score 51, there are 1, 2, 3, 4 people, so I put 4 dot. The score for 70, only 1 data point with 70, so 1 dot. Here, if that was like 76, then there are 1, 2, 3, 4, 5 data point with value 76. And that's the data plots. Now, histogram is very popular. And in histogram, the first challenge is in the horizontal axis or in the x-axis will be assigned for possible values of data points in the sample. This will be the minimum data point in the sample, and this will be the maximum data point in the sample. Now, the next challenge is how do you divide this axis? Do I make, let's say the smallest data point is 50. Do I make this 60, 70, so each interval worth 10 points? Or do I make it 50, 55, 60, so each interval worth 5 points? That will depend on the application. For example, if this histogram represents the score for a test, then it makes sense to each division worth 10 points. So here is the 70, here is the 80, here is the 90, and so forth. So I want to know all students in the 70 to 80, all students from 80 to 90, and so forth. So after you divide the horizontal, Then you count how many data point here in the sample has values that is equal 70 to 80. So if there are 10, then you draw a box here. And the height represent the value 10. And this here you are representing frequency. Then I look in the sample and count how many data points in the sample that have values from 80 to 90. And let's say I have 7. Then I draw a box with height 7 here. So if I draw in this vertical axis the number of data points in the sample that have this value, then this will be like frequency. If I draw percentage, let's assume n here, I have n, there is 100 data point. And students between 70 and 80, there are 10 of them. So 10 divided by 100 is 0.1. So here instead of writing 10, I write 0.1. Then the vertical axis represents relative frequency. And this 7 divided by 100 will be 0.07. And in this case, this axis now relative frequency. And this is the histogram. Now, sometimes you may have data point, talking about this, and let's say you divided this by 10, 10, 10, and let's say this is 50, 60, 70. And let's assume you have a lot of data point between 40 and 50. You have a lot of data point between 30 and 40. This could be temperature. But between 50 and 70, you have few data points. So if I draw between 50 and 60 like this, it's too small. So sometimes we average. So let's assume there are 3 here and there are 6 here. Then this now, the interval will not be uniform. So this whole will be one interval. So there is no 60. So I just say from 50 to 70. And the height here now will be the average of 3 and 6. So 3 plus 6 divided by 2, 4.5. So now the box will look something like this with height 4.5. And then we call this density because I am finding the average of the number of data points in the sample divided by the length of the interval. In this case, if this is one length, 1 unit, this is 2 units. Now I'm drawing the density of the data point in the axis. Most of the case, this will be uniform. All interval will have the same width. And this is an example of the histogram we just discussed. Now, histogram could be symmetric. That means I will draw it like this here. So there are like boxes here, like this one. So you have a peak, and then these gradually go down. And this right half is a mirror image of the left half. Then we call this histogram symmetric. But there are cases where the histogram is not symmetric. So most of the data points are here, then it goes down like this. Now we call this skewed to the right or positively skewed. So you have, if I draw the histogram, looks like this and so forth. So this is skewed to the right. Example of data that is skewed to the right, salaries in a corporation. So you will find most of the employees, their salary around, let's say 70,000. Then you will have few of the employees, the CEO, the managers, their salaries is around 400,000. And usually a histogram that is skewed to the right, if I find the median, it will be somewhere around here, the median. And if I want to find the mean, it will be larger usually than the median. Why? Because this large value will cause the mean to be larger than the median. The median, remember, half of the data point less than the median, half of the data point larger than the median. The other scenario is skewed to the left or negatively skewed, something like this. Example of a histogram that's skewed to the right is the grade of a simple test. So the majority of the student average is 80 and only few students got like 40, 50, 60s. But the rest of the students are around 80s and above. And usually, if you find the median of these, it would be somewhere around here, the median of this population or sample. And if you find the mean, it will be less than the median, somewhere here. Why it is less? Because this data point with low values will drag the mean to a lower value. Other possibility for data points or a sample, it may have not unimodal. That means not only one peak, but it may have two peaks. Biomodel, something like this, then another peak like this. So you have the samples, and when you plot them, you will find the histogram looks like this one. And there are several applications that have this one. In speech, you may find a lot of frequencies here, and then fewer here. This is frequency, and many frequencies here. And these we call them then the foremen for the O, E, A. Now, the second popular way to represent data in a sample or in a population is the box plot. And the box plot looks something like this. The first step, this is your sample. You find the first quartile, and this will be the data for the first quartile. Then you find the third quartile, and this will be, for example, the third quartile. And this will be first. And then you find the median, which is this line in the center. That's the median. And then you calculate the width here, or this range, which is the third quartile minus the first quartile. And we call this range IQR, which is the interquartile range. Then I look on my samples here. I find X-min, the smallest data point in the samples or in the population. And if this X-min equal or larger than the first quartile minus 1.5 of the interquartile range, IQR, then I plot this X-min here, and I will label it like this. As long as the lowest sample is equal or larger than the first quartile minus 1.5 interquartile range. Then I look for the maximum value, Xmax. And as long as Xmax equal or less than the third quartile, which is this value here, plus 1.5 IQR, then I will plot it here, and it will be this one. Now, any data point larger than Xmax will be an outlier, and it will be somewhere here, and I plot it here. Any data point less than X-min is also an outlier, and I plot it here. This line here, this line here, and this line here, we call them whiskers of the plot. And when you look at the box plot, this one, you can learn a lot about the data in the sample. You can find what is the first quartile, what is the third quartile, what's the median, if there are outliers, how spreaded the data point. For example, this is the median. So 50% of the data point is here, and 50% of the data point is here. So if I think of it as a histogram, this is the median, 50% of the data point in this range, so it is somewhere here. This range here is longer than here. So then this is more like this. And this looks like the data for this box plot skewed to the left. This is the box plot, graphical representation of data in a sample. For example, if I look at this box plot, the first quartile is 70, the third quartile is 82, the median is 78, the lowest data point is 52, the highest data point in the sample is 100, and this is an outlier, and I have two outliers here. Now, I just want to emphasize the length of this one will depend on the data in your sample. For example, if you have a data in the sample 95, then you, even though 100 is still less than 82 plus 1.5 the range IQR, which is 82 plus 1.5 times IQR is 82 minus 17 is 12. So that is 100. But let's say in the sample, you don't have 100, you have 92. So what you do, you don't draw this to 100, you draw it to the maximum data point in the sample, which is in this case 92. Just make sure you draw it only to the maximum data point and the same thing to the minimum data point. If in the sample the minimum data point is 60, then this should be to 60, not to 52. Okay, I think here we discussed this before. When I look at this, I can tell this data point is skewed to the left. This is the median, and the range here, which is this, much smaller than the range from here to here, which is this. So this is skewed to the left. Now, comparative box plot, sometimes there is, let's say you have two methods or two systems, and you want to compare how accurate these two systems in giving you the output for the same input. So what you are collecting, you have a sample space of output here. That could be like the design of amplifiers or resistors. And the data here are the values of the resistors. And here the mean is like 100, here the mean is 101. And you collected from these two machines 50 data point here and 50 data point, and you plot a box plot for this one and another box plot for this one, and then you compare. So in one plot you have the two system here, and you can compare the median, if there are outlier, skew to the left, to the right, are the values compact. For example, if this is like here, then definitely the system that make these kind of resistors is better. Why? Because they are all around 100, not much variation, versus this one, even if the 100 here or the 101 here, then there are a lot of variation between different values of resistors. Now the last method is scatterplot, and scatterplot used if you have a sample or a population, but the data points here actually has two values, bivariate. So it has a value x1, y1. This data point has x2, y2, and so forth. And I want to investigate, is there a relationship between x's and y's? So then I decide the horizontal axes represent a data point, and the vertical axis represent another data point. So this could be x and this could be y. And then I plot all these data point here. So they may come something like this one. This is another one data point, another data point, and so forth. And this is, for example, a plot in a soldering machine. The x-axis represent nitrogen content, and the y-axis the strength of soldering metals. And I want to see a relationship. If I have more nitrogen, does that mean the strength of the soldering will be stronger or weaker, or it doesn't make any difference? When I look at this scatter plot, it looks there is a relationship. The more nitrogen you have, the stronger is the soldering of the metals. And that's the purpose of the scatter plot, is just to compare two different variables, x's and y's. And when you plot the scatter plot, let's say, especially if it has a linear shape like this, then I can find an equation. If I know what is x, I can predict with some certainty what will be y, if the data plot here followed a linear line or a linear relationship. Now, if after I plot all x's and y's and I got something like this, definitely there is no relationship between x and y. Why? Because x, this value, I have one data point here of this y. Another data point has different value of y, and this different value of y. So there is no relationship cause and effect between x and y. So if I know x, I can predict y. So there is no linear relationship between x and why. All right, that concludes chapter 1. Next video, we will talk about chapter 2, which is about probability. Thank you.